Hey everyone, I'm Maria Hernandez, a senior in computer science at the University of Tennessee, Knoxville, working with the NorDIC Lab. I've been involved in various research projects in microelectronics and artificial intelligence. Additionally, I served as a TA for several lower and upper level computer science courses over 4 semesters. In today's video, I'll be introducing neuromorphic computing. I'll begin with a motivation and an introduction to neuromorphic systems, followed by a discussion on deep neural networks. Then I'll review spiky neural networks. Lastly, I'll explain the role of non-volatile memories in neuromorphic systems. Moore's law and linear scaling have primarily driven traditional semiconductor technologies. According to Moore's law, 2 times as many transistors could fit onto a chip every 2 years. Meanwhile, the linear scaling principle states that power density stays constant as transistors get smaller. Guided by these principles, engineers have been able to fit more transistors into a chip while keeping the same power density. However, because transistors cannot be indefinitely reduced, this trend has a physical limitation. The end of linear scaling and Moore's law impacts the entire technology sector, particularly the creation of artificial intelligence models, which demand a lot of processing power. Therefore, alternative technologies such as superconducting computing, quantum computing, and neuromorphic computing are being explored as alternatives to conventional semiconductors to attain higher processing speeds, reduced energy consumption, and enhanced computing performance. By simulating the neurosynaptic dynamics of the brain, neuromorphic systems provide an energy-efficient substitute for conventional semiconductor technologies. Artificial intelligence models have been successfully used in several industries, including education, autonomous systems, healthcare, finance, entertainment, transportation, and military. Most current artificial intelligence systems are based on deep neural networks, or DNNs. However, they do not offer the same energy efficiency as spike-based neuromorphic systems. Deep neural networks often use fully connected feed-forward layers and other specialized layers such as convolutional, recurrent, or attention layers, along with nonlinear functional units for the network's architecture. These networks rely on the gradient descent algorithm to update the network's parameters. However, since DNN-based systems require very large datasets to train the model, demand powerful hardware for training and inference, and entail billions of floating point operations during training, they are computationally costly and energy intensive. Contrary to traditional DNNs, spiking neural networks, or SNNs, tend to be sparsely connected, mimicking biological neural behavior through the interaction of neurons and synapses. In these networks, neurons communicate through discrete spikes, rather than the continuous valued signals used by DNNs. Each neuron stores a single value called potential, and each synapse communicates a temporal spike event that travels with a certain delay from a pre-neuron to a post-neuron. Incoming spikes increase a neuron's potential by the synapse weight until the potential crosses a threshold, triggering the neuron to emit a spike across all its post-synapses. After emitting a spike, the neuron resets its potential and becomes non-responsive for a period known as the refractory period. These event-driven dynamics, alongside the network's sparsity, offer an energy-efficient alternative to traditional DNNs, since only the hardware units, or neurons, receiving a spike or event are active. In addition, SNNs leverage address event representation, an asynchronous communication scheme where event addresses, rather than the actual data, are transmitted between the sender and receiver, resulting in energy efficient information transfer. Furthermore, SNNs can run on specialized low powered neuromorphic chips like Intel Logi or Akida, or reprogrammable hardware like FPGAs, and perform well on smaller event based datasets, further enhancing the energy efficiency of these systems. Emerging non-volatile memories or NVMs such as phase change materials and resistive random access memories hold the potential for implementing area and energy efficient SNNs computational frameworks at the device, circuit, architecture, and algorithm levels. NVMs emulate neuron activity by switching between two states, on and off. Simultaneously, they mimic synapse dynamics by supporting a wide range of resistive states between the on and off conditions, resembling the different strength of synaptic connections in the brain. Furthermore, NVMs can be set up in a dense crossbar array, allowing for highly parallel in-memory dot product calculations needed for neuromorphic applications. As Moore's law reaches its limits and AI systems demand increasing processing power, neuromorphic computing provides an energy efficient alternative to conventional semiconductor technologies and traditional gradient based deep neural networks. The energy efficiency of these frameworks is due to their event driven nature, which enables strong performance on smaller datasets and low power hardware. To advance these systems, NVMs show promise in implementing area and energy efficient computational frameworks across the device, circuit, architecture, and algorithm levels. Thank you for watching this video.